but I am pinch hitting today. So welcome back to day 2 of our collection system asset management training. Um, Thanks everybody for being here. We'll go through today's plan here. So you're being welcomed. You got the same instructors today as you did yesterday. I got a couple of housekeeping announcements if you missed them yesterday. Closed captioning is available for you. You can find that in the bottom of your Zoom window in the ribbon. There should be a button for closed captioning. Please take advantage of that if you need it. We're also going to be using Zoom polls today and the Zoom chat. If you've got questions, I got folks who are putting in where they're joining us from as we speak, as they're joining. Appreciate that, everybody. We're going to drop the slides for today's session into the chat here in a minute. And those slides will be available both as a PDF and as a link. If one doesn't work for you, try the other one. Today's presentation is going to be recorded. It is currently being recorded, and you'll be provided with a copy of that as well as handouts and slides and your certificate of attendance. Those will all be emailed to you probably. It might be after the holidays, actually, just thinking of what our current time slots are here. We will take a short break about halfway through the content. You can also, in addition to using the Zoom chat, you can use the Zoom Q&A to ask questions. You're able to ask those questions anonymously, maybe if you're feeling a little bit shy. You can also direct your questions in the Zoom chat to just the hosts and panelists. And then the last bit, which is probably the thing that you are most worried about, is your certificate of attendance for today's session. So we'll be putting a SurveyMonkey link into the chat at the end of today's session, and you're able to take that SurveyMonkey link survey. The start of it will be an evaluation, a couple of questions about what you thought of the class, and then the second half will be your information so that we can send you a certificate of attendance. If you're attending with more than one person, you are able to get a certificate of attendance for all of those people as long as they were registered for today's class. If you have any questions at all about any of that, you can always email ctt@mtu.edu and we'll be able to help you out. There are some chances to get some CEUs from some states. And to do that, I do have a couple of questions for you guys. I'm going to launch 2 polls here. Our first poll, which I'd really appreciate if you could answer, is do you represent a small drinking water or wastewater system? You got a few questions or a few options there, whether you do or don't. And I believe you can select more than one thing with this question. Some of these questions are really helpful for us in terms of the way that we report our attendees, but some of them are also used depending on the state that you're in for how your CEUs get issued. So it's helpful for us, but it's also helpful for you. So I appreciate if you can answer. We'll give a little bit more time for folks to get situated and answer that question. Looks like we've got about 71%. I usually try and get about 75, but because of the nature of this question, I'm going to wait just a little bit longer to try and get as many people as possible to answer. And then I've got one more of these questions, and then I'll turn things over to Greg and he'll get into the good stuff. All right. About 85% of you have answered. I'm going to wait just another second or two here in case we got any stragglers to answer whether or not you represent a small drinking water or wastewater system. Okay. I'm going to end the poll here. We got about 85% of you who have answered. Thank you so much for that. And then I got one more quick question here, which is, can you select the service population for your system? And your choices are less than 3,000 people, between 3,001 and 10,000 people, more than 10,000 people, or maybe you're not a system. And again, these questions are both for us in terms of our reporting, but also in terms of reporting who our audience is, but also for you, for some of the folks who are looking to get CEUs, this information is also important. So we'll give you just another few moments to get your answers in. We'll try and get up to 85% who have answered the same as the last one. And then I'll close things and I'll turn it over to Greg for the rest of today's actual instruction. All right, there we are. Thank you again so much. And you can find the slides have been put into the chat if you need those. And Greg, I'm going to let you share your screen and take it away. Thanks so much.
Thank you, Ingrid. Is my audio and slides coming through okay, Ingrid?
Yep, sounds and looks good, Greg.
Thank you, Scott. I wanted to briefly overview some of the things that we learned about yesterday. Daryl took us through the 5 components of asset management. We looked at the asset inventory, which is a framework to collect data. We talked about asset criticality as a way to analyze risk and prioritize asset actions. We explored the asset life cycle, and we even did an example where we compared an asset where we did all of the required maintenance that would be expected over an asset's life cycle and compared that to not doing the maintenance. And we found out that it actually increased the annualized cost. We talked about levels of service, and we had an example where we looked at a lift station where it was expected to deliver a certain flow and PSI, and we can use that to compare the performance of the asset over time. And we also briefly discussed long-term financial planning, which we're planning to be able to cover the cost of future projects. And we talked about criticality and the higher criticality assets require some type of immediate work, whether it be uh, rehabilitating an asset or repairing or replacing, whereas low criticality assets might only require just routine maintenance. And those assets that are in between, like something that has a high probability of failure but a low consequence, or a high consequence but a low probability, might just require a, a, accelerated monitoring or inspection. We also looked at asset performance over time. We looked at the decay curve, for example, and we noticed that over an asset's performance over time, we get to a point where it has an accelerated rate of decrease in performance, and we want to be able to sort of catch failure modes before they result in outages or further damage. And we're going to get into this a little bit more today as we discuss lift stations a little bit more. But we've found that certain techniques like ultrasound or vibration analysis can help us to detect certain types of failures and replace for example, a small bearing, or adjust the amperage imbalance so that we can prevent greater amounts of damage over time. So we talked about this decay curve and briefly talked about some of the inspection techniques that we'll get into more today. And then at the near the end of yesterday's training, we talked about basically 4 different categories of assessing the condition of collection mains. We looked at inflow and infiltration. We spent quite a bit of time on that, differentiating between what is inflow and infiltration, and how to um, interpret that. And we use the inch diameter mile. We use a concept. Gallons per day per inch diameter mile. We talked about smoke testing, CCTV inspection, and interpreting and coding those results. And we talked about a couple different technologies. electrical scanning, and the sewer line rapid assessment tool. And we use that information to prioritize areas of our collection system that we're going to focus on repairing, inspecting, or analyzing, or rehabbing. And so that kind of sets the stage for today. And as Ingrid said, we want you to be able to interact with, we're kind of separated by this Zoom media. I mean, you're on one side of the screen, I'm on the other. We can't see each other. But if you can engage in the chat, if an idea comes up, just share it in the chat. If a question comes up, share it in the chat, and it'll be recorded there, and we'll be able to bring that up at some point during a Q&A session. Remember the downloads. There's a resource page that has some documents that you'll want to have in your library, actual manuals, and some of them are studies, some of them are blogs, but there's quite a few resources that you can engage with. And by sharing ideas in the chat, you help other learners as well. There might be questions on your mind that other learners have the same type of question. So be sure to take advantage of that. Today, we're going to be looking at the following topics. We're going to start out by thinking of some ways that we can refine the criticality of certain assets. Some ideas that will help us to decide which collection main, for example, is the highest priority. Then we're going to look at some repair and replacement options for collection mains, and then we're going to spend some time on the condition assessment of lift stations. And then as we end today, we'll look at maintenance strategies and how to analyze our maintenance strategies. And then finally, we'll end up with some financial and strategic planning concepts. So I want to welcome you today. I'm glad you're here. And so we're going to get right into this topic of system repair and rehabilitation. And we're going to start by discussing some ways that we can refine criticality. And I want to just check in with everybody. Is everyone able to hear correctly? Or are we going at the right pace? And you can let us know in the chat how you're receiving the information on your end. I'm going to start with this example here, and Daryl shared this example yesterday, where you had a 30-year-old clay pipe, which is represented on the left of your screen, and you can see it has a lot of cracks, and it's even deformed. It's not actually leaking yet, and the pipe on the right, it's a 100-year-old brick sewer and seems to be in good condition based on the inspection. So I want to get some thoughts. If you were in this situation where you had just the budget to repair or rehabilitate one of these mains, which would you choose and why would you choose it? So I'll give you an opportunity to share some ideas in the chat. Thanks everyone for giving feedback on the presentation. And it seems like everyone's able to see and hear. And Daniel says the clay main with the obvious cracks and deformations. And A showing the ones showing signs of existing failure in main A. So everybody is pretty much on the same page here. The one that on the left, the clay pipe with the cracks, everyone is saying that's the one they would focus on. Well, thank you for that feedback. Oh, I want to talk about a couple different things that we can incorporate in our criticality analysis that can help us kind of as a weighting factor. And Daryl shared some of these yesterday, but this image here, there was a main that had failed, um, and it resulted in a serious impact to a transportation route. If this repair would have been planned, crews could have taken time to maybe have a detour. They could have set up a work zone and had materials ready. But in this case, this pipe actually failed, and so they had to make an emergency repair. And you see there's a serious disruption. So one of the things that you can do if you have that GIS map and you have an overlay of your sewer system, your collection system, along with transportation routes. Now, this may not be as bad as it could be. Imagine if this was under a major interstate and it had happened. So one of the ways that you can look at is would a would a main failure disrupt transportation routes or impact business in some way, or kids going to school on a school bus, or so forth. So that's one of the ways that you can weight criticality. So the greater disruption to transportation routes, for example, the higher the criticality rating because it would affect the consequence of failure. And in this case, where a larger wastewater main could contain more wastewater and present a greater threat to the environment or to public health. Uh, Analyzing it from the perspective of how it impacts transportation, a small main or especially a small force main could have the same amount of disruption as a large pipe. And this particular um, main break it was a wastewater main break in a location that resulted in 15 million gallons of sewage into a protected river. So this was also an environmental impact in this particular case. Another way to assess or weight the criticality is just what we just talked about. Its impact on public health or uh, environmentally protected areas, a wetland, a river, a lake, stream. So if a sewer line flows through a densely populated area where or a sanitary sewer overflow or some kind of release of raw wastewater, that would be a higher criticality rating. Or if you see a main that crosses over some kind of river or near some kind of stream, that would be a higher criticality impact. This particular one here that you see on your screen, it released 80,000 gallons of raw wastewater into a creek, and this happened in Florida. And you can imagine in Florida, um, there are some highly critical waterways, for example, that organisms like manatees live in these waters, and that's an example of really an endangered species that are highly sensitive to pollution. Another one is how difficult is it to repair? So you can see that some images here where operators are having to dig down under concrete slabs or to go extremely deep down into a pit to access a wastewater main. Now, if this was a planned repair, uh, they all of the um, work zone and the excavation could be conducted in a safer, um, relaxed time environment. You could have all the materials there that you need to replace it. But if a wastewater main is difficult to get to and you have an emergency breakout, that's a higher criticality, and you'd want to catch that before it happens. And so these types of things, not only is it difficult, it's unsafe for operators, and it can cause longer disruptions and result in a lot higher cost. I've heard some figures, and I've I've tried to track them down and to find the studies to validate these, but in general, as a rule of thumb, emergency repairs can cost as much as 7 times higher than a planned repair. And it kind of makes sense because you're trying to rush around and get materials. Um, you're not being able to take advantage of cost savings. You just need what you need when you need it. You might need, for a repair, you might need some kind of a dewatering pump. You'll need traffic barriers. You'll need safety equipment. Um, and you need all the materials, all the repair materials to be on hand. So um, the impact economically for sure is greater, and a disruption such as an emergency where you have an unplanned break uh, can result in some serious time problems as well. And here's that slide we saw yesterday. We can actually use GIS. We can have a layer that shows our sewer system, and we can overlay that to look at either areas of dense population or areas where our wastewater system crosses over sensitive waterways. This particular image is from Baltimore, and they actually conducted a GIS analysis of the potential for sanitary sewer overflow impacts. And so the dark orange represents areas that either impact environmentally sensitive areas or areas where there's dense populations, and possibly areas such as schools and hospitals, transportation routes, and so forth would even be more highly critical. I'll give you an example here of criticality. We looked at this yesterday. Um, and the criticality for these factors we just looked at would mostly affect the consequence of failure. And we have two examples here. We have a collection main that it's 1,000 foot, 24-inch diameter clay sewer. And we have a 100-year-old 18-inch concrete main. For the clay, the potential or probability of failure is 2. It's not likely to fail, and the anytime soon. And the consequence, however, is 4. It would cause a major impact, probably partly because we analyzed how it might affect environmental conditions or public health, transportation routes, and population centers. So it would have a 4. And this number 2 here, we have a 2,000 foot, 100-year-old main. It's still in relatively good condition for its age. It's a 3, but it could have a catastrophic failure, catastrophic consequence. Most likely it has some extra weighting due to some of those factors we looked at. If we can compare the two, I'm sorry, I have lift stations there too. One lift station has 20 years remaining, and the other lift station only has 5 years remaining. If we take the criticality for each of these, collection one, main number 1 is 2 times 4 gives us an 8. And collection main 2 has 3 times 5, a probability of 3 and a consequence of 5. That gives us a 15. And if we look at those, the collection main with a 15 would be our higher priority. If we analyze lift stations, lift station 1 has a criticality of 8, and lift station 2 has a criticality of 16. So that lift station 2 would be our highest priority in this case. So that would help us to begin planning replacement and repair efforts for those. The the collection main number 2 has the higher criticality, and uh, we have to develop some kind of a plan. We need to know how long it has as for expected life, with the probability of a failure being only a 3. It's not a 4 yet, so maybe we have something like 10 years to plan for that. And the lift station number 2, we only have 5 years remaining, so we'd have to make a financial plan to address that within 5 years. If we look at a asset inventory, some of these things are reflected here. I'm sorry. Here's our lift station number 2. You see it has a 16, and our collection main number 2 has a 15. And so I've circled those under the criticality factor. And so we can make a plan, a financial plan to address those. The higher criticality uh, ones would go into our capital improvement plan. If we have a 5-year or a 10-year capital improvement plan, those would be represented. Um, Now we want to talk a little bit about ways that we can rehabilitate um, collection mains. And there's three general ways I want to talk about. The first is slip lining. You can see that on that listed on the left of your screen. In this, we have a smaller pipe that's basically just pulled into the damaged pipe. Usually, we're using HDPE pipe, which is flexible and the joints can be welded so it becomes like one pipe, and it's just pulled in. The advantage of that, it's probably the simplest and most affordable method, but the disadvantage is it does decrease the inside diameter of your pipe a little bit. Cured in place pipe um, is it's a way of inserting a lining into an existing pipe. This seems to be the preferred method for a lot of pipe rehabilitation. It does not affect the interior diameter as much as slip lining. It's essentially just renewing your pipe, and it has a 50-year life expectancy. You pull in a liner that is impregnated with some uh, curing chemical that will cure into a hard pipe. The disadvantages of cured in place pipe, CIPP, is if you have a situation that doesn't allow the liner to be pulled in effectively, like for example, a collapsed pipe. You couldn't pull a a liner into a pipe that's collapsed, for example. Um, and also, if you have anything that disrupts the curing period, it takes about 24 hours for CIPP to cure. And so, if you had, for example, active infiltration coming in, it would interfere with the cured in place pipe. So um, often there needs to be some kind of way to dewater around the pipe, and you might even need some bypass pumping to go around the repair area so that the wastewater upstream is able to be pumped downstream of the repair section. And you might need to have that pumping go on for a whole 24 hours. Pipe bursting is a way of pulling a piece of pipe while bursting the old pipe. So if you have some concrete pipe, the bursting head, this is on the right of your screen, comes in and destroys that pipe while it's pulling in a new pipe. This is the probably the most expensive, but when you get done, you have a brand new pipe, and it's of the same diameter or at least of the old pipe. It is a little expensive, and a disadvantage can be if you have other nearby utilities near that bursting head, they could potentially be damaged because that bursting head is it's pneumatic, and it is producing enough energy to damage and remove that old pipe from the path as it pulls that new pipe in. So, for example, if you were really near a water pipe or really near some other utility, like a gas line, you might not be able to use this method. So we'll look a little bit more at cured in place pipe. You have a pipe that's damaged, it has cracks, but the pathway is not obstructed. You would clean it and evaluate the pipe to make sure that it fits into the scope of what CIPP can be used for. Then you would have possibly the need to bypass pump around the repair site. In some cases, and Daryl has had experience with this, in some cases, your collection system may have enough storage where you can just block off that section that's going to be repaired and allow the upstream piping to basically be like a storage tank for the wastewater as the repair is being conducted. But if not, you would have to have some bypass pumping around the repair site. The liner is pulled in and inflated, injected with its the liner is injected with resin. It's inserted into the pipe and then inflated in some way so that it expands out to the pipe diameter, and then it's cured. And there's different ways that people use to cure it. It can be with heated steam, but there's other methods that can be used. It could even just naturally air dry if you have the right conditions. After this pipe is inserted, it's blocking off all of the interconnections, such as service connections coming from homes. So a robotic tool is used to go through and restore all those service connections. I read about some other problems that can occur with CIPP pipe, and that includes connections in manholes can end up leaking, and so sometimes you have to go back and grout those interconnections in manholes because that's where the pipe terminates, right? And so sometimes you might have to do some grouting around those those terminal ends. And here's a little diagram that shows the CIPP being essentially inflated uh, with either steam or water, and then it's cured with either steam, in some cases ultraviolet light, or just natural air. And this is an image here. You can see at the upper left, the construction crew is inserting that liner. You can see it just comes out just looking kind of flat. It's flexible. They're inserting it into a collection main from looks like from manhole to whatever the downstream manhole is, and they're pulling it through. And on the bottom left of your screen, you can see the before and after picture of a CIPP project. That left pipe is it's pretty much gone. That section of the collection main was basically the ground around the pipe, and you can see the after picture that pipe has been restored. And on the right of your screen, you can see that little robotic tool that goes through and reestablishes the connections. Now, if you had to isolate a section for repair work uh, or to conduct bypass pumping, you can use these sewer plugs. Some of them allow you to pump through them, um, and but all of them will inflate in the sewer. And these sewer plugs have to be sized. We looked at these a little bit yesterday when we talked about smoke testing, but they need to be the right size for the pipe that if it's a 24-inch pipe, you need a 24-inch um, sewer plug. Let me move something here. So you can essentially isolate the area. We'll look at slip lining a little bit more. When you conduct slip lining, you're basically pulling a smaller HDPE pipe. It's a plastic flexible pipe into the damaged pipe. Now, to complete the process, there's a little gap likely between the new HDPE pipe and the older pipe, and this is filled with grout here. And you can see a image of a device that's being used to push the smaller pipe, HDPE pipe, into an older pipe. And it's guided. And here's an example of the end of a pipe being pulled. So you're winching it through while you're pushing it. And here's a little pushing device that could be added to like a backhoe or something that can allow you to grab on and manipulate the pipe, push it in, or insert it without damaging the pipe. Here's another image of a pipe being inserted into an older pipe. And at the end, an attachment is added, and grout is placed around that slip line pipe to seal it. So those are the processes. This slip lining, as you can see, you lose some capacity of your main, but it's pretty straightforward. If you pull it in, you don't have to spend any time curing like you do with CIPP, but you do lose some diameter. Pipe bursting. Here we have a little diagram. You can see the bursting head coming in. It's destroying that old pipe and pulling in a new pipe. Here's an example of what a bursting head might look like, and there's going to be some kind of a winch that is putting constant tension, and you can see that little hole at the end of that bursting head. That's where the winch would be connected. And you can see a little bit. I showed this image before, but kind of a close-up diagram of how the bursting head would move that old pipe, destroy it, and move it out of the way. And here's an actual image here of a pretty large pipe being pulled in. You can see the winch pulling that in, and it looks like the operators are there, and they're going to be, or the construction crew is there, and they're going to be disconnecting that as uh, the journey of that bursting head is coming to an end in that location. These are trenchless technologies that we just looked at. However, as you can see, that some excavation did have to occur to retrieve the bursting head and some basically some potholing at the initial location where you start and the terminal location where you end. The other option, if you're not using trenchless technologies, is open trench construction. Um, this is the most costly and the most time consuming. You have trenches. You have to use shoring to protect operators if the trenches is in an unstable area or if it's over 5 foot, and you're disrupting roadways and so forth. Sometimes it's the only option. Obviously, if you're going under something like a highway or roadway, um, you you'd want to use trenchless options. But sometimes there's no other choice but to do an open trench installation if those other methods won't work. The advantage of open trench installation is you're going to be able to do more perfect work probably. You're going to be able to make sure the bedding is right. If you have bedding that has sharp stones and it's uneven, that can contribute to pipe failure. And so you'd be able to do good work. Um, However, it's the most costly and most time-consuming, labor-intensive option. But in some cases, you might not be able to use things like pipe bursting because it interferes with other nearby utilities. And in some situations, you're not able to use CIPP because the conditions are such that the lining might collapse. Like, say, for example, if we're not able to stop infiltration and the pipe cannot cure correctly, it can result in something like you see on the upper right of your screen, where you install the lining and it collapses, and then you have worse problems. And of course, slip lining might not be an option because you can't afford to have the pipe be smaller. You need the full capacity of the pipe. And we're going to go to our first poll here. And the pole is a you have a trunk main, and it's already at the minimum diameter required. And it has a lot of leaks and cracks. It passes under a highway and along a river. And so what method do you recommend? And I'm not saying there's any one right answer. This is for you to think about what method would you use. And while you're doing that, I'm going to be looking at the comments and see if there's any questions or thoughts that you've shared. And I see we're up to 79% participation in the poll. Give another 10 seconds here if you want to get your answers in. And then I'm going to address some of the questions and comments you might have. So I'm going to end the poll and share the results. And 66% chose CIPP because it rehabilitates the main without reducing the capacity. Um, and 12% said slip lining because it will best seal the main. And 20% said pipe bursting because it will allow a new pipe to be installed. And 2% said open trench construction is necessary. Um, well, thank you for that. I was kind of thinking along the lines of B myself, uh, but I'm not going to say that's the one right answer uh, because there are a lot of other um, potentially a lot of other considerations to think about. Now, I saw some good comments here in the chat that I wanted to talk about before we get too far. And I see, Scott, you shared the resources again. Thank you for that. Timothy said in his utility, they had old brick mains and manholes in a state-run facility where he was employed. The system was in good condition at nearly 100 years old prior to closing a few years ago. That's amazing. I imagine those old bricklayers back in the day, well, maybe they weren't old, but the bricklayers back then, they must have done some amazing work for that to last so long. And so thank you for sharing that. And the next one here Brian asked, pipe bursting. Can the bursting head drive through a partially or fully failed um, pipe section? And it should be able to. The if it was fully failed, um, you might be depending on the basically the basically the tunnel that's left through a certain section, but the pipe bursting should be able to to go along the same path as the old pipe. I imagine there's rare circumstances where the pipe head can get off course. If anyone has ever had had an experience like that, please share it in the chat. But it's supposed to follow along that pathway. And I saw another one here um, where someone said, "Will this work on steel or cast iron pipe?" And as from everything that I read about and hear about, is an old cast iron pipe um, is brittle, and especially if it's old and needs to be replaced, it probably has some serious corrosion, and it's not that strong. So yes, it works great on cast iron pipe. If you had some kind of a heavy steel, I imagine that would be challenging. But uh, if you had, something like a ductile iron pipe, that would probably be a lot newer pipe anyway, and probably wouldn't need to be replaced. But I mean, if you had something that was really super strong, I imagine you know, you'd have to maybe use a different method. But for old cast iron pipes, it works good. I'm looking at see if there's any more comments here. And I see some of you are putting your answers into the chat. That's great. All right. Well, thank you for all that. And we're going to move on here. And before we leave this slide, though, um, can you think of other information that you would like to know about a situation like this that might influence your decision of what you might choose? I know a couple of you said that it might not be appropriate to use trenchless under a highway. Um, Actually, I think it might be kind of the opposite. If you're going under a major highway, you'd probably want probably prefer um, to use trenchless technology rather than disrupting the highway. But you are right also by thinking ahead and saying this trenchless, we have some kind of a bursting head, for example, or something going on underneath the highway. You're right in thinking about what could the trenchless methods damage, because you're not there to visually see it happening. So other utilities and possibly culverts and stuff are under the roadway, and you're thinking rightly on the right along the right line about what do we want to prevent from damaging. And uh, Leah is saying that you'd want to know about the age of the main and the condition of the highway and any upcoming highway work. Well, that's a great thought. Um, and Leah also mentioned the pipe depth. How deep is the pipe? Oh, Joe said how you would like to know about the daily flow rates for bypass pumping. Well, those are good thoughts. Impact to users based on the downtime for repair. Excellent. Those are all excellent things that you're considering there. Thank you for sharing those. All right. I'm going to keep a track. I have a little, I have the clock here on my phone, so I make sure we're staying on track. And I chose B, but there's no one correct answer for that. Thank you for the discussion. We're going to move on to talking about lift stations here. And specifically, we're going to think about what are the components of lift stations? Why are they there? What happens if they go out? And but more specifically, what are some ways that we can use to assess the condition of lift stations? We talked about this a little bit yesterday when Daryl was talking about failure mode effects analysis, and we looked at all of the different components that are in a lift station that have to work, and there was quite a few. There was the power coming in, there was the control panel, the level control system. In this image here, we see the level control system is floats, and we have a pump and a motor. In this case, it's a submersible pump where the pump and motor are one. We have a force main, and that force main has check valves on it so that the the water that we just pumped to the higher gravity sewer doesn't flow back into the wet well as soon as we pumped it. So we want to consider some of these things. If a lift station were to quit working, it can result in sanitary sewer overflows. It's you might say it's almost like a breach. It's a intersection point in the collection system where you're conveying wastewater from a lower uh, portion back to a higher portion in the collection system so that it can continue on flowing by gravity in most cases. Those are the ones that are situated out in the collection system. And of course, you have different variations. There's lift stations at the headworks, for example, because by the time you get to to the to the treatment plant, you're usually pretty low because their collection mains have a slope. It might be only a 0.5% slope or a 1% slope, but over a long distance, if you have a fairly flat area, your collection pipes are going to get deeper and deeper and deeper. And that's another reason to install a lift station is if your collection pipes are just getting so deep where excavation is just so expensive and unrealistic, you have to dig down 30 feet to install a collection main. The lift stations can help to minimize that, so they can actually save you money. So we have the gravity collection would be going on and going deeper and deeper at a certain slope, and we lift it up. So there are some advantages. It can avoid that costly excavation. It can also you can also transmit a pretty good flow using a smaller pipe because you have the pumping is at a certain pressure and a certain flow. So your force main can be smaller. Maybe you can convey as much flow as a 12-inch gravity just through a 4-inch pipe because you're pumping at a higher rate. However, if it goes out, you can have overflows, backups into people's uh, basements and so forth. You have to have some kind of emergency backup equipment, whether it be a generator or some kind of a emergency backup pump. It also can create hazards because if you need to work on it and you have to go down into the lift station wet well, that's a confined space entry. And there's toxic and explosive gases, oxygen deficiency that you can encounter. There's basically two types of lift stations. I say that two categories of lift stations and a bunch of variations in between. But you see the wet well on the left, that just simply means that the pumps are underwater. There's two submersible pumps there. That wet well is never going to be, if you have a submersible pump, you're never going to want to pump it down to zero because the submersible pump needs a little bit of water to keep it cool. On the right hand side of your screen, you can see a portion of the lift station is in a dry well. The pumps are in a dry area that allows operators to maybe make some adjustments and repairs and checks without actually having to have a full confined space entry procedure. In our collection system based lift stations will typically have two pumps, and they call this a duplex pump installation. This gives us, there's two reasons for this. Um, First of all, it gives us some redundancy. If one pump goes out, at least you have one pump that's still working. But the one of the main reasons is so we have a wide range of flows. One of these will be the lead pump. It comes on when the wastewater reaches a certain level. And what's interesting too, you can actually see, if you notice at the top, you can see that someone has written lag on that float. And it's harder to see the bottom right of that image. Someone has written lead on that float. So if the wastewater is coming in like a normal rate, and the level gets to a certain point where it lifts the lead float, it'll turn on the lead pump. And if there's no excessive flow, The lead pump will pump the flow down, and it will, once the float straightens back out, it goes off. And then it alternates for the next cycle. The other pump will be the lead pump, and it might exchange every cycle, or it might trade places between lead and lag at a different uh, interval. But they change places. One's the lead, one's the lag, then they switch places. Now, if that lead pump is not able to handle the level or the flow, and it gets up high enough to move that lag float, then the lag pump will also come on. Then you have both pumps pumping. And so you have more pumping capacity, and it pumps the wet well down faster. So it allows you to handle a wide range of flows. And these floats can become coated with grease and fats, kind of like a fatberg developing on the float, cause them to be heavy and they won't lift properly. So periodically they need to be cleaned, and you can take a rod and lift these up and make sure that they work. You can do some testing every so often on these and make sure that they're operating the appropriate functions. The lead should turn on the lead, and the lag should turn on the lag. And the high level pump should operate the high level warning, whether it's a light on top of the lift station panel, or a auto dialer, whatever the alarm system is, it should operate that. The wet well is normally sized to have a 20 to 30 minute detention um, area time, and that can be partially reduced if you have a VFD. A VFD allows you to to handle a higher range of flows. You're trying to minimize pump cycling. And when engineers design a wet well, they'll say, hey, we don't want these pumps to be turning on more than 6 to 10 times per hour, for example. That would be the upper level of cycling. You don't want your pump turning on, every 30 seconds, because it's hard on the pump. It uses too much energy. It's not efficient, and it will reduce the pump's life. So you want it to be sized appropriately. So some of the things that can happen that can disrupt that is if you start having a lot of I&I, inflow and infiltration, that adds a lot of extra water to these lift pumps that were designed for a certain flow. Then all of a sudden your cycling increases, and it results in additional wear. There's a concept of the active volume in the lift station wet well. This is the difference between the lowest level that's expected to be, where it gives you room for cooling the pump, and the upper level. That would be where both lead and lag pumps come on. And then you have some extra range in that high level that gives you a little bit of time if there is an outage. So that area above the active volume before it actually overflows, that's your time that you have to take some kind of action. So you're designing the size of the wet well for the expected flows, plus any kind of emergency factor, and a little bit of storage for outages. And the active volume is the distance between off and both pumps on. And we're designing um, the amount of wastewater that we're going to allow to collect in the wet well to also ensure that pump our pump turns on no more than 6 to 10 times per hour. Okay. That second box, by the way, you see the wet well on the left of the image. That second box in the image, that would be where your check valves are. As the wastewater flows out through the force main, there are some check valves that will keep the water from flowing back into the wet well. Those check valves can become clogged, and we'll talk about that in a moment here. Here's an example of how the different floats might be used. In this case, we have a lift station that has 3 pumps, but you can see there's a low level float that would come on uh, that would tell you, hey, you don't have enough water. There's not enough water uh, to keep these pumps cool, and it might also initiate some kind of alarm system. And then you have the lead and lag on and off floats, and then you have a high alarm float, and you can see how they're arranged. And those have to be neatly, you don't want installed. You don't want the lines to get tangled up. You don't want the floats to become tangled with grease. And in the image on the right, you can see two submersible pumps, and you can see there's some guide rails that allow the pumps to be installed without actually having to enter into the wet well. Those pumps can be pulled up and they slide right up those rails. And when you install them, it's the same thing. They slide right down the rails and they connect with the piping. You can see the floats on the upper left of that image, and you can see the incoming influent wastewater um, pipe on the left. And how you would set these, you would have a little distance. Uh, for example, the high level alarm might be 6 inches above the lag pump on here. So that both pumps come on and they can't keep up. You want to know that right away. Hey, we're not able to keep up with this. Something's wrong. The lag pump on might be something like 12 inches above the lead pump on. The lead pump comes on, it can't keep up, it needs some help. And then the lag pump comes on. These are just some ideas about what you could do. And the lead pump on and off, that's set to handle normal flows and at a distance that would allow it to pump enough so that it doesn't have to start more than the maximum cycling rate. Sorry, I went a little bit too fast on that. So you don't want it, that lead pump on to lead pump off, the distance there uh, is the distance that you would want to pay close attention to so that you have under normal operation, you have the minimum cycling rate. There's some different ways to control the levels in the tank where, in other words, when do the pumps come on and off? And besides floats, floats are good because they don't require an external power source to run them. I mean, they still need power at the panel, but the the float itself, it just operates by gravity. So when the water level goes up, the float tilts and it makes an electrical connection that, but it doesn't actually have power to it. But some of these other types of devices actually do require like a SCADA type system and power to it. And one is a pressure transducer. You can see on the left, you can see an image of a pressure transducer, and on the right shows you the location of the pressure transducer at the bottom of the well, and it's measuring the pressure imparted to it due to the level of water above it. And so that's going to send, depending on the level of water, it's wastewater above it, it's going to send somewhere between a 4 to 20 milliamp signal. The 4 would be when it's at its minimum level, and 20 milliamps would be at its maximum level. Um, so that's going to transmit um, those readings to the control panel, and it's going to decide what pumps um, need to come on or off, and if there's higher or low warnings that need to come on. Those can be clogged. You have to check them once in a while. Another method is ultrasonic, where it sends out a beam that reflects off the surface of the water. You can see one installed there on the left. It's hanging down. And on the right, it shows you a diagram of how that beam goes out. It's high frequency sound waves, and it kind of fans out into a cone. So you have to make sure that that cone doesn't intersect any other wires or objects in the wet well, because it could potentially give a false reading. This works on the basis of time of travel. So the time that it takes for the sound waves to go to the surface of the water and back is the time, and it it converts that into a distance. And so you can see a little image here. The beam goes out, reflects back. And so if you have anything like equipment that's interfering with the cone, it can affect it. But it also uh, can be affected by foam on top of the water. And so it has to be calibrated to make sure it's giving an accurate measurement. But it's as long as it's calibrated, you don't have excessive foam issues or anything that is intersecting the path. It's a very accurate method. There also can be radar sensors. It's sending an electromagnetic pulse instead of sound waves, but it works on the same concept. And one of the advantages of the radar sensor, it's not affected by foaming. It's going to reflect off the water source even if there's foam on top. It can, however, be affected by any source of electromagnetic radiation, such as, for example, if you had a VFD controller that was close enough to it, it could potentially affect the accuracy. So, and in a panel here, we have, of course, circuit breakers and things like motor savers, the actual leads coming in for the pump, the power coming in and the power to each lead, pump lead. But one of the most important things is the relays. That the relays, for example, are the connections to the floats, the float controls, for example, and they're going to be responsible for turning sending the signal to turn the pump on or off, sending the signals, for example, to the motor starter to engage the pump. There's also going to be the alternator in there that's going to alternate between the lead and lag pump. And there's going to be alarm systems and electrical connections. This particular one, you can see at the top of the panel, there's some little lights there. That's to let you know if the pump is having an alarm condition. And on the upper right, there's actually a transmitter as an antenna that will transmit so that you could log in with a SCADA or you can get a notification if there's a problem with the pump. Here's an example of someone reaching into the wet well to they have a long rod with a little angle at the end of the rod, and they're lifting each of the floats to test and make sure that they're working appropriately. And we have our second poll here, and I think it's probably about time for a break after this poll. Um, so our question is, what could happen if the float control system malfunctioned in a lift station? Hey Scott, are we able to set a timer for the break? Do we have that functionality, or should we just keep track of it on our own?
Yeah, we should be able to do that.
Okay. Um, I want to ask everybody that's online, would you like to have a short break and get through the material faster today, or would you like to have a 5 minute or a 10-minute break to give you a little more time? Let me know in the chat if you need a 10-minute break, and Scott will set the timer appropriately once we finish this poll. Okay. Daniel and Muhammad said 10 minutes, so we'll do 10 because if anyone needs 10, I don't want to rush you. So as soon as I get done with this poll, Scott, we can set the timer. Does that sound good?
Will do.
We have 77% participated in the poll. I'll give another 10 seconds to see if you can get your answer in if you're still thinking. All right, 79%. I'm going to go ahead and end the poll and share the results. And almost 86%, well, yeah, 86% said all of the above. And between 6 and 2% chose one of the answers. And you know what? You're all right. And but specifically, all of the above could definitely happen. And if you think about the things that could happen if the float control system um, doesn't cause the pump to come on or doesn't cause it to shut off, all of the above could happen. And so we'll go ahead and have a 10-minute break. And when we come back, we're going to look at some more in-depth inspection methods for lift stations. I thank you for all the great comments that you're adding today, and I'm looking forward to more. Thank you, Scott. Oh yeah, T Timothy, maybe E didn't get included on the poll. I'm not sure, but if all of the above wasn't available, I apologize for that. But still, you all got it right. Every answer was correct. See you in 10 minutes. Okay, we are back. I hope you had a great break. And we were talking about what could happen if the floats malfunctioned in a lift station. And we concluded that all of those things could happen. In a lift station, you'll normally have a panel that shows the hour meter. In this one, for a duplex pump, you see there's two hour meters for pump one and for pump two. And that is important. The amount of pumping that's done can be used to calculate the volume of water that's pumped. It can also be used to compare to the actual volume that's been metered that has been pumped. So you can look at how well your pumps are operating. Also, because you're alternating between lead and lag, these pumps over time should have about the same amount of pumping. And in general, if you compare them, they should be within 10% of each other. If there is a difference bigger than 10%, it could mean that one of the pumps is either wearing out, there's a clog in the pump. Uh, if there's just one check valve, um, it may not be the check valve, but if both pumps had increased pumping, it could let you know, hey, there's might be a problem with the check valve. It's stuck partially open and we're having to repump some of the water that we just got through pumping to the force main. Um, so you want to record that. It's best to record it daily and then compare those readings probably at least once a week to see how. But you could also check it daily to see how close they are. And there's where you would look at the hour meters, and so how much did it pump each day is a good piece of information to know. Also, you'll have a HOA switch usually on a lift station. HOA means hand, off, and auto. So if you turn it off, everything's off. If you have it on hand, the pump is just on. It's like a light switch. You turn it on, the pump's going to run until you turn it off. And when you put it on auto, then it's able to respond to the automatic control system, the floats, for example. And that's where you're going to be running it most of the time on auto. When would you run it on hand? Well, you'd run it on hand, especially if you're doing testing, so like a drawdown test. You want to see how much it draws down the wet well over a certain period of time. And so there's HOA switches are there, and if you're doing some testing or you have it off, you want to make sure that before you leave, it's back on auto. There's a little close-up picture of what a handoff auto HOA switch might look like. In a drawdown test here, it's a way to check the flow rate. We were just at a utility, and we were looking at their lift station, and they had a magnetic meter, a mag meter that would actually uh, it would let it would record the flow the flow rate and the amount of flow that was going out of the lift station. But they also would do a drawdown test periodically just to check the meter and make sure it was accurate. But if you didn't have a meter, this would be your way to check the flow rate that's being produced by each pump. And over time, the pumps could wear out. There could be some kind of problem developing, and this is just one more check that you can use. And so you basically know the size, the diameter of your wet well. Let's say it's 36 inches diameter, and you pump the water down 12 inches. Well, you should be able to use the volume formula to calculate how much water was actually pumped over a certain period of time. Let's say we pumped it down a certain distance, or we pump it for 1 minute, 60 seconds, and then you look how much is pumped and divide it by the time, and you can get your um, actual gallons per minute of flow that's being pumped by that lift pump, and you can check both of them. So that to do that, you would use um, the hand option, and you could let it actually build up with wastewater. And in some cases, the crew will actually add water to the wet well to bring it up to a higher level, and so they can get a good measurement. Because if it's real low, the volume is taken up partially by the lift pumps, so you're not that takes away from the volume that you're pumping. But if you get it up a little higher, then you can calculate the volume better because there's no other objects under the water. And you can also use this as a way to compare pump efficiency over time. This is not actually the efficiency equation, but they let's say you have the rated gallons per minute, or the amount that the pump would produce when new. So you could take the actual pump. Let's say we installed it 10 years ago, and when it was brand new, it would pump 150 gallons a minute. And now when we check it, it's pumping 123 gallons a minute. We could see how much, how much difference there is, what percent difference is there, and then we can investigate why is that? Is it because the motor's wearing out? Does the impeller need to be adjusted? Is there something clogged? Is the force main becoming clogged? Something like that. When you go out to a lift station, there's certain things that you could record if you have access to it. Uh, like for example, the number of pump cycles, if you have access to that information, pump cycles per hour, that would be good to know. How long it's actually running, how much it's actually each pump is run. Uh, the wet well level, is it running or not? Has there been any alarms? What is the total flow that it's been pumping? Those are all good pieces of data to record when you go out to check on a lift station. If you have increased run time, I mentioned this before, but there is a check valve on the force main, and it allows water to only flow in one direction from the pumps out to the force main. And we don't want that water flowing back. So if it tries to flow back from the higher collection system through the force main and back into the wet well, well, you'd be double pumping that water. And so if a check valve becomes kind of partially stuck open because there's grease and debris there, the water is flowing back in, and that could be one of the reasons why you have increased runtime, because you're not only pumping the new water, but you're pumping a portion of the water you just got through pumping. But of course, there can be other reasons for increased pump time. It could be that your pump is a capacity is reduced. Your pump is partially clogged, and it's having to pump 10 minutes because of, for what it used to pump in 5 minutes. You could have some kind of excessive inflow and infiltration coming into the wet well. And of course, over time, as your community expands, you're going to, the amount that you're pumping could increase also. If you have 100 more homes on your system, it's going to increase the wastewater that's being applied to the system. And also, if we have things like solids that are coming in that are causing problems with our check valve, there's certain things we can do. We can add things like screens to keep things like rags out, or grinder pumps to keep things that are, like large solids or fatbergs out. Normally, a pump uh, is a lift pump, a submersible lift pump is designed to pass a certain size of solids, typically at least 2.5 inches. And here are some examples of the kinds of things that can cause problems. If you have problems with solids, you might have to have a grinder pump to solve that. Fats and oils and greases entering, that's more of a situation where you might need to go out and ensure that restaurants and so forth are properly maintaining the grease traps. You really don't want grease to be going into your system, but you could also install some type of aeration. Rags can really wreak havoc on pumps. They can tangle up. Um, Flushable wipes are not really flushable, and things like rags, and people even sometimes will flush diapers down the toilet, and those can really wreak havoc. They're not biodegradable, and they can end up causing some clogs. So rags, you're wanting to screen those, and there's even certain types of cutter pumps that can help to solve some of those problems. And here's an example of that cutaway of a submersible pump, and the inlet there. I don't know why this particular image has the arrow going out, but that hole at the bottom is where the water comes in, and then it goes to the impeller and out the discharge, and that should be able to pass a solid that represents a sphere at least 2.5 inches in diameter. Could be larger depending on the type of pump that you're using. And you can see the motor is up above that. And that's one of the reasons why we want to maintain a certain level of wastewater in the wet well so that this pump can be cooled. It's sealed, and you want it to be sealed from water coming in and destroying the electrical components, but also you want water around it so it can be cooled. Certain types of submersibles are dry run submersibles, where there's a special jacket that circulates water, and you can actually run them in a dry situation because you have water circulating. Those are a little more expensive. Sometimes they'll be in pump stations and intended to run dry, but they also could survive if there was a flood, so they could operate out of the water or in the water. Here's some examples of different types of cutter pumps and grinder pumps here. And here's an example of some operators that did some innovation here. They added a bar screen where the wastewater comes in to collect any rags. So then they can just go up, they can look in the lift station, and they can take some kind of a rake and just pull the rags off of there that have collected on the bar screen. And they also added an aeration system to break up grease because they were having problems both with grease and with rags. And they got tired of replacing pumps. And so they took some action and they did something about it. And so this is that aeration system is just some perforated pipe, and they have a pressurized air system, and it bubbles up through the wastewater to break up the grease. And periodically, you're going to want to go out to the lift station and clean it. Clean you see a crew here on the upper left, or they have basically a sewer cleaning truck, but they're using that truck to pump down the lift station, uh, vacuum out any debris that have settled at the bottom of the lift station, and they're spraying down the floats to make sure that they're not coated with grease and so forth. On the bottom, uh, a couple of photos more to the right. In this particular lift station, they found a mop head that had fallen in there, and they were worried that that was going to get into the pumps. So they lowered a hook with a rope, and they were able to identify that and pull it out. So they were able to do that without actually having to go in and have a confined space entry. So those are the kind of things that you might see when you when you pump the lift station down and clean it. You might find things such as that, and that would have been probably uh, not something they'd want to put into their vac truck, so they decided to hook onto it and pull it out. Having a pressure gauge on the force main is another way to assess the lift station. Here we have a situation where the water is being pumped through a force main at a certain flow and pressure. Over time, if the pressure increases, it might mean that there's debris or something else that's impeding the flow. If you have decreasing pressure, it means the water might be going through a leak. So those are good things to look at. And here's an example. On the left image here, we have a lift station diagram. You see the lift pumps at the bottom, but they go up, and the upper right of that image with the orange, there's your check valves. And you can see an actual, on the right of your screen, you can see an actual vault with the check valves coming out, and then they both come out. Each pump has a separate check valve, and then it goes to the force main. On the force main, there's a pressure gauge there. And so that could be a transmitting pressure gauge, or it could be one that just reads out that hopefully you can open it and see it from the top without having to go in. And that is a good item to have to check the function of your force main. As I mentioned before, lift stations require some kind of backup power. If we have a power outage and the lift station stops working, we could have a sanitary sewer overflow, and we might have to have a backup generator. This requires additional operator maintenance and knowledge, and it can be something that you have to manually turn on, or it can be set to automatically come on during a power outage. But it's something that you have to check the oil levels and the fluid levels. You have to do a test once in a while to make sure it works. So it just installing it is not the end of the story. Operators have to go out and maintain this, change the oil and so forth. You could also have some kind of a bypass pumping unit. This is a mobile unit where the operators can uh, move it around. And if you just had a few lift stations and you had time, you have large enough wet wells, you could go around and just pump them down. Right? There's a system not too far from us that does this very exact thing. If they have a power outage and it's going to last for a day or so, they'll take their portable pumping unit and they'll hook up to lift stations. And you notice there's a couple of pipes uh, that are extending up from the lift station. In order to use something like this, you would have to have the piping connections that allow you to hook the pump to the lift station. That would be the only thing. That is another um, asset expense that would be well worth it that you can use bypass pumping at the particular lift station. Here's an example of pulling a pump, and it's sliding up those rails that we looked at before, and usually it's done with a crane winch. You're not having to grab onto it and lift it. This could potentially be a dangerous operation. You don't want to lift it by the electrical cable. You want to make sure the power is off when you're doing this. And there's a safety grate there that you're only opening that just to bring the pump out. And that safety grate there is to prevent operators from falling in. And there's a major cause of injury at lift stations where operators go in, they drop a tool in there, and they try to go in and they fall or they expose themselves to dangerous atmospheres. And so you want to, anytime you're dealing with any kind of wastewater, you want to also use personal protective equipment because raw wastewater, has hazardous pathogens in it. And then we're going to talk a little bit about some of those condition assessment strategies that Daryl talked about yesterday. We'll look at vibration analysis and ultrasound and infrared and some electrical testing that you can use. Is everybody doing okay out there so far? Are we going too fast or too slow? Are you enjoying the training? You hearing me okay? Okay, thank you. Thank you. I'm glad you know the we we try to design these trainings so it's not um it's not so long to be unbearable. Still, 2.5 hour training is a lot of time to sit in front of the computer. We know that the um, the material takes at least 5 hours to go through, and stretching it over 3 days would make it more difficult for operators to be able to attend. And so we're trying to make it so that the length of time of each of these sessions is not overbearing, and we're not requiring you to log on so many days. But any feedback you have on that, how we can make these better, we're be sure to mention that in the evaluation, and please fill out the evaluation. Now we have the vibration analysis here set up. You can see there's a sensor that's installed right where there's a bearing inside that pumping unit. And we're monitoring the vibration over time of that bearing compared when it's new to compared to later on. Is there an increase? And there's a thermal image where we're looking at the bearings, the heat coming from bearings and mechanical points there. And on the left, you can see an operator that's using ultrasound. He has the earphones on and also a readout, and it's telling you that it's comparing the noise when the bearing is in good condition, brand new, to increases in noise later on. You can also use ultrasound actually to lubricate bearings. You can apply just the right amount of lubricant or grease. Say, for example, you have a little grease gun and you're adding grease. You can just apply just enough to take the sound away. So it's pretty amazing technology. Here's some examples of some infrared images, and you can see that definitely more heat is coming out of the bearing areas. That's the whiter hot, the lighter colors or the hotter points. And this is showing some impending bearing problems. Vibration analysis here, there's different points that you would measure at. So you're comparing increases in vibration, but very small vibrations, much smaller than you would detect with your senses. You know, it's very, very sensitive vibration, and it will give you a early warning if something is about to fail, or you could different things could happen besides just a bearing. You could have a damaged impeller. Maybe there was some water hammer, or maybe there's some cavitation going on. It would sense those. It could be that if you have a coupling, if your motor and pump is separate, connected with a shaft, that it might not have perfect alignment between the motor and the pump, and that could cause problems as well. And vibration analysis can help with that. And here's an example of vibration over time. Here you see that there was some cavitation on the left-hand side of that graph, and it caused a spike there that you could see. And then on the right of that graph, and this is more of a conceptual graph, it shows this increasing trend over time because there's a bearing or something going on, and when it gets up to that alarm level, it's going to let us know. In this situation, that alarm level is because we have continuously installed vibration sensors that are always there. And but it doesn't have to be continuously installed. It can be like a handheld device that you apply to your mechanical equipment and just test it periodically, maybe once a quarter. So an increase means that there's something going on. There's a bearing starting to fail. It's not lubricated properly. There's cavitation. There's misalignment. And so if you have a continuously installed system, it would convert uh, the vibration to some kind of a 4 to 20 milliamp signal, and you could monitor it in real time as well as look at trends over time. And interesting little tidbit that I found, that last bullet point on the bottom, excess vibration in submersible pumps actually can shorten the seal life. On a submersible pump, there's seals that keep water out. If the seal fails and water gets into the pump, that's the end of the pump. And so excess vibration actually uh, interferes, loosens those seals. And that's one of the things, if you have a contractor that comes out and pulls lift pumps periodically, that's one of the things they'll do. They'll check those seals and maybe replace the seals. Um, if you have a in-house way to service submersible pumps, you'd have to have some specialized tools and some specialized equipment, because submersible pumps are sealed, and even the electrical line going into the pump is sealed, and so it takes some special tools and some special knowledge. Most of the time, in small utilities, we'll just hire a contractor that comes out and checks those periodically, keep them running. Ultrasound, there's some basic decibel levels that you can look at. Now, if you compared to new, if it increases 8 decibels, it it indicates that's pre-failure, or it might not even indicate a failure. 8 decibel increase might just mean that you need a little bit of lubrication. You need to grease the bearing. Now, a 12 decibel increase means that we're right at the beginning of a failure mode. And this is long, long before we would sense it with any other means. A 16 decibel increase means we're well into a failure condition. And if we get up to between 35 and 50 decibel gain, when we compare the sound when it's new to now, if that sound has increased 35 to 50 decibels, it means that something bad's going to happen. The bearing's going to go out. The pump or motor is going to fail. And so we would monitor that over time. For electrical testing, there's some things that are recommended here. First of all, you want to measure the amperage draw. If you have a three-phase motor, you can look at that image on the bottom left, and they're measuring the amperage draw with a clamp style amp meter, and it gives you a reading in amps for each of the three legs. For three-phase voltage, you have three hot leads that are 120 degrees apart in the phase. And so you want each of those amperage draws to be within 5% of the average. So you'd add up the three amperage draws, excuse me, divide by three, there's your average, and then you compare each leg to the average, and it shouldn't be more than 5%. If it is, you can rotate them. If you label those three leads coming into that pump motor, you label them A, B, and C from left to right. And if you rotate them, you have to rotate all three, A to B, B to C, and C to A. Then you can recheck. If you're above five, you can rotate them and recheck. And there'll usually be one orientation. There's three ways that you could have it. There'll be one orientation that has the least amperage draw, but the amperage imbalance could be from the motor, or it could be from the electrical supply. Also, you can measure the insulation resistance of the pump windings or the pump wiring, but the pump windings requires mega ohm testing, and you're looking at, can a high voltage, low current get through the insulation on those wires to ground. So eventually, over a long time, as a pump ages, or if there's overheating all the time, it can break down that insulation. If electricity starts getting through the pump insulation and to the ground, it's eventually going to cause that pump to arc out and fail. Also, voltage imbalances are a bigger deal than amperage imbalances. Sometimes you can have transient voltages that imbalances that are due to other components coming on or off. It could be due to um, bad connections, and it could be due to something going on with the service voltage. But a voltage imbalance more than 1% is a bigger problem than an average imbalance of 5%. So you can check all those things, and you can also measure the imbalance between uh, the resistance of the leads. So if you're going to calculate the amperage imbalance, here's how you would do it. We have an example here where we measured the three legs of the of the amperage draw of the motor, and one was 11.1 amps, one was 12 amps, and one was 13.2 amps. Now you notice this is amperage draw, so guess what? You're doing this when the pump motor is running, which means that you're dealing with high voltage. You might have a 240 volt pump, you might have a 480 volt pump. So guess what? It's very dangerous. And also, when you open any kind of panel, there's always the risk of arc flash, which is very dangerous. So you notice this operator, first of all, has gloves, has protective equipment, probably a face shield as well as protective clothing, and they're probably standing on a insulated mat to protect themselves. So you want to make sure you have the right kind of training before you start reaching into a panel. And the good thing about the this style of amp measurement is you have this clamp, and you don't have to actually touch any actual live wiring. It just wraps around the insulated lead. So that's an advantage, but you have to be very careful. We take the average. So we add these all up, divide by 3 because there's 3 legs, and we add them all up. It comes out to 36.3 amps. We divide it by 3 and we get 12.1 amps as the average. And then we can compare the imbalance for each one. For example, we take the average and find the difference between that and L1, 12.1, the average minus 11.1 divided by the average. And we convert that to a percent, we get 8.3. So that's above 5%. L2 is within specification. It's only 8.8%. And L3 also is a problem. 13.2 amps and L3 minus the average divided by the average gives us an imbalance of 9.1. So we'd probably want to try rotating these um, to see if we can get uh, a better amperage draw balance. So we'd rotate L1 to L2, L2 to L3, and L3 to L1, and we recheck. We could also measure the voltage from each lead. And if it moves, if the imbalance moves with the lead that's coming in from the power supply, it means it's due to the power supply. But if it stays in the same location, it has to do with the pump. So those are important things to do. Here's an example of someone testing the mega ohm resistance. Basically, we're looking at, can electrical current get through the insulation and the winding all the way to ground? And it helps us to know if there's any kind of shorting out or if the insulation is deteriorated over time. And you can also, I'm going to show you on this topic, I'm going to show you another slide to compare the mega ohm readings. But resistance of the motor leads. And you can actually do this with the pump installed. You can do a lot of these tests with the pump installed. You don't have to take it out. But in this case, we're showing a pump out. But the resistance between the motor leads, you can test the resistance between 1 to 3, 2 to 3, and 1 to 2. And basically, you're looking at the path of the current that goes from the lead all the way through the windings to the next winding. And basically, the resistance should generally be between about 0.3 to 2 ohms, not very high, but a little bit of ohms. Right? 0 ohms would be that's a there's no resistance at all. Where infinite amount of ohms mean it's an open circuit, the wire is broken. Um, so you want a little bit of ohms, but not much, between 0.3 and 2. But for specifics, you'd want to look at your pump manual. So if you had 0, it means it's going right to ground. And if it's infinite, it means you have an open circuit that's broken. And you also can perform the same kind of equation like we just did to see if there's any imbalance. And you also want the resistance to also be within 5%, so you don't have imbalance. Now, I just promised that we were going to look at mega ohm. This is checking the resistance of the windings. And there's several values here. And this is a lot of information on this chart, but what we're looking at is mega ohm values. A mega ohm is 1 million ohms. And for electrical power to go all the way through rubber insulation or the insulation that's in the winding, you'd have to have a very high voltage. And that's what they do with the mega ohm tester. It's a high voltage, but low current. And it's trying to get through the insulation. So basically, if you have a new motor, it's going to be a high mega ohm value. When it wears out, it's going to be less. In general, if you're assessing older motors, it should be at least ideally greater than 10 mega ohms or 10 million ohms. So The minimum, however, that you could still run it would be 1 million ohms or 1 mega ohm. And here's the good condition, motor in good condition that for sure can be reused, greater than 10 mega ohms, 10 million ohms, and the very minimum, 1 mega ohm. If we are below um, half a mega ohm or 500,000 mega ohms, that definitely means we have some damage that we have to attend to. We'd have to consider planning a repair. Another way that we can assess our lift station is by looking at the wire to water efficiency. Basically, what we're doing is we're comparing the electrical power going in to the water horsepower that's being produced. And we can figure out the water horsepower by knowing the head, which is another way of saying the pressure, and the flow that's being produced by the pump. So I'm going to give you an example here. We have a pump motor that's operating. It draws 18.65 kilowatts of power, of electrical power going into the motor, but it produces a flow of 800 gallons a minute and 90 feet of head. Um, Head can be converted to PSI. 2.31 feet of head equals 1 PSI. Now, if we wanted to convert the motor horsepower, the kilowatts of power to motor horsepower, we can divide by this conversion factor, 0.746 kilowatts per horsepower. And you notice the kilowatts will cancel out and we're left with only horsepower. So if we take that 18.65 kilowatts divided by 0.746, we get 25 horsepower is going into the pump, has electrical energy. Now the water horsepower, we use the horsepower equation. The flow in gallons a minute times the head and feet divided by 3,960. That's our conversion factor to go to horsepower. And if we multiply that out, 800 gallons a minute times 90 feet of head divided by 3,960, we get water horsepower. So 25 horsepower is going into the motor as electrical energy. What we're getting out in terms of flow and pressure is 18.2 horsepower. So you see we've lost some horsepower there because there's some turbulence in the pump. There's some electrical energy that's lost um, through through heat. There's some friction in the pipe and in the pump, and so we expect to lose some power. But we're going to compare these two. We're going to take the 18.2 that's coming out divided by the 25 horsepower that's going in and look at the overall efficiency, the wire to water efficiency. And this particular pumping system has 72.8% efficiency. Now that might not mean that much just by itself. This, for all we know, this could be a brand new pump that has a 72.8% efficiency. The important thing is to compare this over time. You'd like to ideally know this, the wire to water efficiency when the pump is new, and then be able to compare it over time. Maybe you do this once a year in your, or every 6 months or every quarter or something like that, and you can compare if the pump is losing efficiency. If it is losing efficiency, then you would want to know why. You could check things like the electrical imbalances. You could check the impeller adjustment and things of that nature to see is there any leaks and see why are we losing efficiency. You could also use it as a means to compare your service level of the pump and to know when you need to rehab it or replace it. There's a kind of a higher level of technology that they're using too. Contractors, certain contractors can perform this, and it's called motor current signature analysis. And I have a link there that you can look at some examples here. And in the references, I believe there's a couple of documents that talk about this. But basically, they're not looking at the amount of voltage or amperage here. They're just looking at the current, um, the like the phase, the electrical waves that are being produced by the electricity going into the motor. And they can actually detect some amazing things. If you look at that image, that graph on the top, you see there's a spike there. And what that spike represents is when the rotor is turning, one of those little bars in the pump rotor was broken, and it was creating that spike in that graph. So that motor is turning at a high RPM, but they can see that little spike. And they said, you know what? It looks like one or more of the rotor bars is broken. And sure enough, when they pulled the pump, you can see that image on the bottom middle of your screen. There's a rotor bar that's broken, a rotor bar that has been broken. And they can also detect things like if the rotor is a little bit off set from the stator, um, and they can that image on the lower right of your screen, if it's off a little bit, it'll also cause a certain type of signature. And people that are trained in this can look and detect certain types of problems. It's really kind of interesting. This is kind of like a supplement to condition assessment for pumps. If you have more than one type of information, you could use composite scoring to score the condition of electrical components like this. For example, you might see that you do a mega ohm resistance and you see that insulation resistance has been decreasing over time. But you look at the history and you see that the pump is operating 8 hours per day, no problem, and it's supplying the head and flow that we need. So the first one shows that we have some decrease in efficiency, but it's functioning well as far as our record of breakdowns, no history of breakdowns. We did a wire to water efficiency, and we see that over time we've lost about 5% of the efficiency. It decreased from 70% when it was new to 65% now. We look at the cost to replace the pump motor. It's about 8,500. That's including the installation. And so when we analyze it, we could have some kind of composite scoring. We look at the remaining useful life. It's 35 years old, and it was expected to only last 25 years. So we're beyond the expected life. So we could give that probably a poor, number 4 for poor. The results of the inspection show that we have decreasing insulation resistance and decreasing efficiency. We also give that a poor. 4 for poor. However, the performance history, no history of breakdowns, so we give it a 2. How easy or practical is it to maintain? Well, in the old days, with large pumps, we'd probably have it sent off to be rewound. But nowadays, with the speed of manufacturing, it's probably cheaper. It's only $8,500 to purchase it and have it installed. It's cheaper just to replace it. And how well is it doing in the service level comparison? Well, it's providing the flow and pressure that we need. And so we give that a 2. So if we add all those together and divide by in this case, we have 1, 2, 3, 4, 5 elements of rating, divide it by a 5, we get an average rating of 3.2. So that's an example of how you could use maybe some composite scoring. Maybe not exactly like this, but you could develop your own way of using composite scoring to assess the different types of measurements that you might have. If you improve a pump or a system, you can actually measure how much money you saved by looking at how much efficiency you've improved by as a percent. One of the ways you can do this is to measure the kilowatt per hour energy used for every million gallons of wastewater pumped or treated. So as an example here, we had a facility here. It was using 260 kilowatt hours for every million gallons of wastewater that's been pumped. But then operators, they did some actions on this pumping facility. They adjusted the impellers, they replaced the check valves. They even installed new pumps to match the system curve, and they installed VFD controllers so that it would be just idling when there's low flow, and they wouldn't operate at 100% unless there was a really high flow. So they're just using enough energy for what they need. So they improved it, and now this pumping system uses less kilowatt hours to pump that same million gallons of wastewater. So if we do that, we could actually look at the efficiency increase, the 260 kilowatt hours that it used to take, minus the 175 kilowatt hours we're now using. We can look at the difference, and we divide it by the original, divide it by 260, and we are 32.7% more efficient now. So we saved that much electricity as well. If we look at how many kilowatt hours, that 260 minus 175, that is 85 kilowatt hours. We can multiply that by the number of hours the pump runs, by the number of dollars that it cost um, per kilowatt hour, and we can actually show a cost savings, how much we actually saved in dollars, real dollars and cents, and of course that could be used to determine whether whether we're going to actually save money by doing this project. We're going to go to poll 3 now, and this poll 3 asks us which of the following indicates the need to repair or replace a pump motor. Everybody doing okay out there? I see we're up about 73% here. Let's give another 10 seconds here, see if we can get our answers in. Last call. All right, I'm going to end the poll here at 78%. And the majority of you, 43%, said the mega ohm reading is less than 250 ohms. And that would definitely signal that we have insulation breakdown, because we want it to be at least 10 million ohms ideally, and the very minimum that we can accept is 1 million ohms, so 10 million ohms. The amperage imbalance, we want it to be less than 5%. We don't want it to be greater than 5%. So 3% is okay. B, the resistance measurements for the motor leads, we're normally good between about 0.3 and 2. but we want it to be balanced as well. So those numbers are actually okay. And for the A, for ultrasound, remember 8 decibels. It really only it might be a pre-warning that there might be a failure mode, but it's more than likely just telling us we might need a little lubrication. If we have an increase of 16 decibels or more, it tells us we're definitely into a failure mode. In 35 to 50, it's going to fail at any time. So thank you for all of the participation, and definitely the mega ohm reading less than 250 ohms is the thing that tells us we need to replace this motor right now. When we go into a lift station, if we have to go in, you notice that this image on the right, there's a tripod there. There's an there's another operator that's observing and is able to uh, provide help to the operator if the operator gets in trouble that's entering. Um, but lots of lots of hazards. Every hazard you could think of associated with wastewater operations, it's all inside the lift station. There's electrical power. There's the chance to fall. There's liquids that you could drown in. There's dangerous gases, explosive gases, um, confined space, limited means of entry and exit. So every possible danger is in the lift station. And so if you do enter, you want to follow confined space entry procedures and uh, and be in contact. Someone needs to be in contact with emergency services. You need to have a tripod and a way to rescue someone. You don't want to jump in and start helping somebody without having like an SCBA, for example. Many instances of people that go into an unsafe manhole or lift station, and the atmosphere, they don't know it, but it contains a one breath death, one breath and you die. About 25% of all confined spaces have a one breath death. And you rush in to help your buddy or your coworker, and you just add to the pile of bodies if you don't have a rescue plan in place already. And that tripod at the top is meant to hook to your lanyard gear, and it's a way to rescue someone without having to enter. In general, you want to have after you test the atmosphere for uh, oxygen enrichment or deficiency, you also have to test for toxic or explosive gases such as hydrogen sulfide, and you have to ventilate the space. And in general, you're ventilating at a level that changes the air in that volume completely every hour, 12 times per hour. There's a concept in engineering that relates to safety, and it's called the hierarchy of controls. If there's a hazard, the highest level would be completely eliminating that hazard, and the lowest level would be not doing anything to eliminate the hazard, but just providing workers with uh, personal protective equipment, PPE. So let's say you have a wet well, you don't do anything to make it better, but you have a self-contained breathing apparatus, you have the safety line, you have the tripod, um, and of course everything else in between uh, is modifications to either change the way people work or isolate people from the hazard or so forth. The most effective is elimination of the hazard completely. Here we have an example here of a operator that did have to go into a wet well, and you notice they have some safety equipment, um, a way to rescue them if there's a problem. I assume the power is off. I assume they're ventilating that space, but they have to enter, and so it's a hazardous operation. If you redesigned, you might redesign that lift station so that the operator can enter into a dry well instead of having to go into a wet well. So that would be an example of redesigning and eliminating or partially eliminating the hazard. Uh, as I mentioned before, lifting the pumps of a submersible pump out of a wet well, it just slides up a couple of rails, and you notice that lifting chain is stainless steel, so it won't corrode, so it will remain in good shape. But this is also a safety mechanism, so you don't have to enter the wet well. Ways of maintaining the sewer include running a combination sewer cleaning truck, and you see there's a jetting head on the upper left and a vac on the lower left. That's used to you pull the materials to a manhole with the jetting head, and then you remove them with the vac. In general, when you clean a sewer, you start an upstream manhole with the jetting head, and it has a high pressure spray backwards, and you pull that debris back to the manhole, and you use the vac to pull it out. If there's roots, you can actually add attachments that will cut roots onto that jetting machine. And there's a variety of maintenance strategies. We have preventative maintenance, which is based on time or amount of use, where you do it every so many gallons or so many days. Uh, and there's predictive, where you actually maintain on the basis of inspection. That would be something like you have a ultrasound, and it shows the bearing is possibly going to fail within the next year, and so we make plans to replace that bearing. And then run to failure is also a valid strategy because there's certain components like a relay. It's like a little black box, and there's nothing you can do to maintain it. But you just, when it fails, you just have another one nearby and you plug it into the panel. Reactive and deferred shows that there's something going on. Reactive would mean that our infrastructure is aging and we have some problems and things are breaking down. Deferred means we have some problems with capacity in our utility. We have financial problems or managerial problems or technical problems. We don't know how to do it. The management doesn't see the importance of it, or we don't have enough money to do it. We can actually do some measurement called the planned maintenance ratio to see how much of our maintenance time is planned and how much is reactive. The planned maintenance uh, ratio is the planned maintenance, the hours of planned maintenance divided by the total hours of maintenance that we conduct. And we'd like that to be as high as possible. If it's lower, it means we have some reactive maintenance going on, unexpected breakdowns that have been occurring. And here's an example of how we might use that. We had a utility that had 2,250 hours of total maintenance, and 1,500 of those hours were planned. So we can do the ratio by taking those 1,500 planned divided by the total of 2,250, and we see that we had a planned maintenance ratio of 67%, which is not bad. And over time, as you improve your infrastructure and your inspection techniques, you would expect that to go up because you're planning instead of reacting. Now, I'm going to give you a chance to calculate this yourself here in the next poll. And we're asking, we have a utility that has 1,000 hours of planned maintenance, but the utility also spent 800 hours fixing unexpected breakdowns. So we have to do a little extra calculation here. We have to first figure out what's the total maintenance. 1,000 hours of planned plus 800 hours of reactive gave us a total number of maintenance hours of 1,800. Then we can take the 1,000 hours of plan and divide it by the total. 1,000 divided by 1,800 gives us 55.6. And over time, we'd like to reduce the amount that we spend on reactive. Let's try poll 4 now. What percentage of the maintenance time at your utility is reactive? And you can do a quick calculation in your head, or you can just estimate. All right, we're at about 71% here. I'll give a 10-second warning here because we're going to wrap things up here pretty soon. We're almost at the time. I'm going to end the poll. And the majority of you said 40% said between 26 and 50% is reactive. You're spending a significant amount of time on reactive maintenance. And some of you said less than 10%. That's great. And greater than 50% of your time is reactive. That's kind of like fix it when it breaks. Uh, and between 11 and 25%, 28. So that's a transformation over time that will improve as you build capacity. And capacity can be described as three legs of a stool, kind of. You have technical, that's the performance of your assets and internal knowledge to operate and maintain. The managerial capacity is planning and coordination. That's what you're learning about now. Asset management is a managerial process. And financial. Do you have enough revenue to cover all these things? And this is an EPA concept, TMF capacity. And you can see in this little diagram, it lists some different types of capacity. It kind of gives you some ideas what each of those are. What it actually looks like, how does it actually manifest in the things that are important to operators and managers? Do we have sufficient pumping and treatment and collections capacity that operates continuously? Do we have redundancy and backups? Do we have a sufficient trained workforce? That's managerial. Adequate policies and standards. And the financial side, do we have adequate revenue to fund operation and maintenance and to cover debts? Do we have a capital improvement plan with reserve funding? So that's how it actually manifests the things that are actually important to us. There's a couple ways that we can use to assess our financial capacity. One is the operating ratio. It's the ratio between the revenue and the amount that we receive through rates divided by the operating expenses. Obviously, that needs to be greater than one or at least one. If it's less than one, we don't have enough money to even cover our basic operating expenses. And if it's equal to one, we just have just enough. But we want it to be greater than one. It means we can cover our operating expenses plus some capital investment. And typically, funding agencies will want to see an operating ratio of at least 1.2. But if you can get it a little higher, it means you have some extra funding for reserves. The debt service ratio is also a good ratio to look at. It gives you your capacity to cover your debt payments. And you're taking the net revenue. Net revenue is the income minus the expense, and you divide that by the annual principal and interest, and you'd like that to also be at least one, but a debt service ratio of 1.2 or greater is even better. And when we actually bring the annual cost of the CIP plan to our budget, we would do something similar to what's it going to cost to replace it divided by the years remaining. So for example, we have a VFD that we're going to install to run our pumps. That's going to cost 25,000. We're going to do it in 8 years. Um, so we take the 25,000 by 8. And so we're going to want to contribute $3,125 per year for that project. And that is going to go into our budget. And so if we had that represented in a CIP plan, we would see it here. We're going to do that in 8 years, and it's going to cost us 325. And all the different projects is going to result in a number that we're going to contribute to the budget each year. And a CIP plan could be a 5-year. Some people utilities do a 5-year and a 20-year, where the 5-year is more action oriented and they've refined those replacement costs a little bit closer because it's not going to change as much in a 5-year period as it will in a 20-year period. And the 20 is more long-term planning looking and for the larger projects. But over time, the replacement cost will go up due to inflation. Not on every asset every year. Some assets get cheaper. For example, a computer would be, a computer that has a certain capacity now, something like in the gigabytes and extreme speed and so forth that we could buy for $500 today. 10 years ago, it would have been a significant expense. So th certain things go down in cost, but a lot of things that are cement and steel and construction based, they go up. Here's an example of an asset that cost 500,000, and 20 years later, when they needed to replace it, it's costing $876,753. So if we just replace equal to the depreciation, we're going to fall short. So we have to find a way to account for that shortfall. And if we were going to analyze how well we're doing in a utility, it would be a good idea to calculate both the operating ratio and the debt service ratio. And here's an example: our cost, our annual operation cost, 250,000. Our income is 325,000. Our debt principal is 60,000 plus interest gives us a total debt service payment of 62,500. We can calculate the operating ratio by taking the income divided by the operating cost, gives us a 1.3. But for the debt service, the debt ratio, we calculate the net income. That's 325,000. Our income minus our expense of 250. It gives us 75,000 of net income. Then we can calculate the debt service ratio, and we see we have 75,000 income divided by our total debt payment, 62,500, and we see our ratio is 1.2. So that utility is doing just right. But as prices go up, rates have to go up too. You can also look at your audit reports. In the audit reports, you'll have a balance sheet. It shows you if your overall equity is increasing or decreasing over time. The statement of cash flows will be showing you where your cash is going and coming in from. And your income statement gives you your profit or loss. That net income is important to know. So those sheets can give you the information that you need. And we have our final poll of today. We have a utility that has expenses of 250,500 and revenue of 325,600. And we want to ask, what's the operating ratio? And this, our time is expired, but I'm going to hang around for another few minutes for questions. I'm a little slow today, sorry. We'll give a 10-second warning here. Try to get your answers in. Oh, Ruben, you can't see the poll. Go ahead and put your answer into the chat if you can't see the poll. All right, I'm going to end the poll here and share the results. And the majority of you said 1.3 was the operating ratio. We're going to bring this thing to a close here. And that is the correct answer, by the way. We took the income divided by the expense. In your slides, you'll see a link to a funding guide, um, and you can click on that link, and it'll go to your region, and you can find all the funding sources. It actually has contact information and websites where you can find uh, funding sources for your utility. And we're gonna skip these last couple slides. You can look at that on your own. It's just a quick example of strategic planning, how you could bring the major projects that you have into a strategic plan, and an idea that we can change the culture of our system by having proactive planning that results in asset management plan and ways to improve our utility. And so here's an example of what the funding portal looks like. It brings up a map, and you click on your state, and it will bring up information for that state. And so I'm going to end now, and if there's any questions, I'm glad to try to answer them. Thank you for being here thank you for all those excellent comments. I see some comments that I didn't even get a chance to uh to read out loud. Do we have any questions, Scott, that you see that we should address?
I don't see any, Greg.
Scott, you think that means that I did a terrible job and nobody has any questions, or I explained it so well, there's nothing else to be asked?
I think you covered it pretty well.
See how nice Scott is? I
And
appreciate.
just as a reminder, I did put in a link to that attendance self-certification and course evaluation survey in the chat. Please fill that out within 24 hours, and that's how you'll receive your certificates of attendance for today. Actually, that'll be covering both days.
Thank you, Scott. Yes, please fill out the end of course survey. That really helps us out, and it also helps you to get a certificate. And Nicholas, you're not seeing the link for the. Are you not seeing the link for the certification?
You may have to scroll because there's been a number of comments put in the chat since I pasted it, but I'll put it in there again right now.
Thank you, Scott. Thank you, Joy. And thank you for all the nice comments. Don't forget the slides and the references sheet uh, is in the chat somewhere too, if you didn't get that. But I don't want to I don't want to stimulate a bunch of chat right now because I want everybody to be able to get the self-certification survey that Scott just posted. I want you to be able to get to that. Really appreciate you all being here. You had such good comments. And I think there's some people out that were attending today that have more knowledge than us, and we appreciate you sharing your expertise with the group.
We can hang out for a couple more minutes if anybody has any questions. Otherwise, thanks for attending today. We'll give it a few more minutes. As I see more and more people logging off, we'll probably call it. So thank you again. Okay, I think we're going to call it for today. Thank you again, everyone, for attending. I hope everybody has a great rest of your day and a great holiday. Thanks again.